Good morning. Good morning. Excellent. We're back in high school. Okay. Actually, you are in more ways than one because you fell for a trick. Okay. So, what did we do last class? We did something about BST. So we started with binary trees, and then we transitioned to binary search trees. And why did we transition to binary search trees? Transition to binary. Yeah, because we wanted our logarithmic behavior, right? So we were using this recurrence. We're using the recurrence that says t of k is equal to t of k divided by 2 plus c gives us a logarithmic behavior, right? Yes? That's what we did. And the way we accomplished that, so what do we need to get that? Okay. The way we're going to get that is we're going to subdivide the problem in 2 each time, but we also have to make sure we only do a constant amount of work, right? And so the constant amount of our work is we're going to check for equality against the root value. That's a constant amount of work. And if it succeeds, we're done. If it doesn't succeed, basically we're going to do ternary comparison, as it's called, right? A three-way comparison. If it's equal, we're done. If it's less than, we recur. If it's greater than, we recur. And therefore, we know that we only do a constant amount of work. Okay? And each time we subdivide into a subtree, and it's a binary tree. So we get a subtree, and that's how we get our recurrence. Yep? Good. Okay. If you're at high school computer science, you probably taught this. Some of you may have seen this in high school, yes? Great. Okay. And of course, like 2 or 3 of you have realized this is completely false. Why is it the case that if I recur on a child of a binary tree, the child is half the size of the binary tree? Is it? No. How bad can it be, as a matter of fact? Here's what I want you to do. I want you to talk to your neighbor. First, introduce yourself, talk to your neighbor, and tell me what the most degenerate, that's not a judgment here, okay, it's a technical term. What is the worst kind of binary tree you can have from the perspective of one subchild is half the size of the whole tree? That is, the 2 subchildren are equal in size. What is the worst you can have that is furthest from that? Go.
And then decide all the way and decide all the one the other child.
Okay, in 5, in 4, in 3, in 2, in 1, and we're back. And draw me your tree. Show me your trees. Yeah, show me your trees. Show me your trees. Everyone draw a tree. Okay, how many of you vote for this way? And how many of you vote for this way? It doesn't matter. Okay, yeah, we won't get into the politics of leading left and leading right and right. So, the point is, a degenerate tree is basically just a list, right? It's a binary tree, but all of one side could just be empty, 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 and that's just a fancy way of writing a list. What in what we have done has prevented that from happening? Absolutely nothing. Could you give me an example input, a sequence of inserts that would cause that? Sequence of inserts, yeah. Yeah, one that's already sorted in either order, right? If it's sorted one way, you'll get it one way. If it's sorted the other way, you'll get it another way, right? So if I said insert 1, 2, 3, 4, 5, I'd get something that's 1, 2, 3, 4, 5. Insert 2, 5, 4, 3, 2, 1. I'd get something. So in fact, it's not even that it's not possible. It's actually very possible to end up with exactly that behavior. Okay? So a binary search tree is not at all sufficient for getting the logarithmic behavior that we set out to get. Right? So last class was basically a giant piece of trolling. Right? What we're going to do today is to talk about how to fix that problem. What we need we're again strengthening our invariant, right? We talked about invariance, we talked about strengthening invariance. We're going to strengthen it further to define that, which is a balanced binary search tree. That's what we had implicitly assumed all along. If we can get a balanced binary search tree, then by definition this recurrence is going to hold. Okay? So I haven't told you how we're going to get one, but if we can get one, then that's exactly what's going to give us this recurrence. Okay? Good? So far so good? You see where we're going? Now, there's a common thing you'll run into in computer science, which is we'll always write these recurrences in this very precise way that everything is subdivided by 2. Now, of course, what that means is the only things you can construct are then sizes of powers of 2, and there's a lot of things that are not powers of 2, right? And of course, the powers of 2 get more and more oddly. I mean, the first few of them are pretty good, right? 1, 2, 4. Yeah, I skipped 1. That's okay, right? Yeah, 8. Yeah, I skipped a little bit. Then as you get bigger and bigger, it's not so practical, right? So you can't keep padding things to make things the size of power of 2. So we need to relax these definitions a little bit, and I'll show you one particularly useful relaxation today. Okay? So just be aware, when we do the theory, we're going to do it in terms of power of 2. In practice, that's not a practical size for many cases, most things actually. Occasionally it works out fine. Most things it doesn't work out, so we have to relax those definitions a bit, and the math will be a little more complicated. In 19, we're not going to deal with the exact difference in the math. As you get to more advanced classes, sometimes it will actually matter, but for the most part, it won't. Okay? Good? Fine. I want to make one administrative comment, by the way. What I'm trying to do is I'm trying to keep both doors somewhat open to get some cross ventilation in here. Right? Just to get, there's people wearing raincoats that are wet and stuff and it's humid. So I want to get some cross ventilation, but I don't want to keep that door completely open because there's a lot of noise that comes from the elevators and people out there. So I'm going to try to prop this door semi, but not all the way. If you get here past 9:59, come in the other door. I'm going to try to keep the other door. Just go directly. If that door is not completely open, it means it's propped and probably class has begun. Just come in through the back. Is that okay? Just remember that, and if you'll forget, that's okay, but just remember that in the future. Okay? So I'm just going to try to prop this a little bit so we get a little more. Okay, good. Okay, so how do we get balanced binary search trees? Well, I actually identified the critical problem. The problem was, it's not looking up, right? Looking up doesn't care anything about the shape of the tree, it's just look up. Right? So the fact that every binary search tree is a balanced binary search tree, in fact, every one of these is one of these. In fact, every one of these is one of these, means at least some of the programs we've already defined for these we can use right here. Like lookup works fine on this. It doesn't care about the size and shape of the tree. It's just going to do its lookup job. So as long as you have a binary search tree, which every balanced binary search tree is, right? Then a lookup that ignores one branch is perfectly okay over here. Does that make sense? So we can reuse a bunch of code. Our problem is really with insert. Insert, as it's currently defined, is not doing anything to give us the invariant of balance. It's giving us the BST invariant. It's not giving us the BBST invariant. And we have to make insert work a little bit harder. You see that? Thoughts on that? Good? You see the game we're playing here now? Yeah.
If your insert is done incorrectly and it's horribly inefficient, can combining insert with the BBST end up actually being less efficient than just using the list?
Well, so first of all, I don't quite know how to parse that question, because if your insert is incorrect, then all bets are off. So I don't think that's quite what you meant, right? I don't want to talk about incorrect algorithms. There's lots of them, and some of them are actually very efficient too. Right? The insert that never inserts anything is constant time and very efficient, not so useful. So let's try to rephrase your question a little bit.
Insert works correctly, but...
In terms of functionality,
yes,
but does not do any balancing, right? Okay.
No, if it works correctly, but really slowly.
Well, it depends on which insert you wrote. So I mean, the naive insert is correct, but in the worst case, it's not sort of slow. It's not any slower than a list. right? Essentially, the worst case is you get a list. The insert we currently have degenerates into giving us lists, right? Like you said, the already sorted input is an example of that. It just degenerates into giving us lists, okay? They're just lists that end up consuming a little extra space because there's this extra empty sitting around that's doing not much of anything, right? So there's, in terms of time, it would be a list. It degenerates into a list. In terms of space, it's like off by a constant. Does that answer your question? Good. Okay. All right. So, yes.
How are we exactly defining balanced in terms of?
Oh, we haven't talked about that at all, right? I'm going to get to that, right? What I've told you so far is I'm assuming balanced means that the two things are exactly half, right? The two subchildren are exactly half, and I have to make that a little more crisp now. Okay. So what we're going to do, so I have to do two things. I have to give you a better definition of insert, and I have to even tell you what balanced means, keeping in mind also that, exact half is not always practical. Okay? Okay. Now, for what I'm going to tell you today, there's typically, when we talk about these kinds of tree algorithms, there's usually two kinds of measures on trees that we care about. One is the size of the tree, which means how many nodes are in the tree. The other is the height of the tree, which is what is the tallest part of the tree. Does that make sense? Height of the tree versus size of the tree. For what we're going to do, it's going to turn out to not really matter. It matters some, but it doesn't really matter. That recurrence doesn't care. It doesn't tell you whether k is the size or k is the height. Okay? But what I'm going to do to be unambiguous is I'm going to talk about heights of trees. We could do what we're doing today, redefining it in terms of sizes. I'm going to do heights because it's actually visually a little more obvious if we do it in terms of heights. Okay? So I'm going to use heights, not sizes. Good? Okay, first thing. Could you define the height of a tree? Everybody, I want you to talk to your neighbors for about 30 seconds and tell me how you would define the height of the tree. Think about writing code. Okay? We did our definition, right? We can just define height on BTs because height is a well-defined concept on any of these things. Height of a BT, go.
Yeah, so you have to because you might have something that here
Okay, 5, 4, 3, 2, 1, and we're back. So, how many cases do we need in our definition? Yell it out.
2.
Why?
Because there's two parts of the data.
Because there's two parts of the data definition. So what do we do in the empty tree case? What's the height? 0 or 1. 0 is because we don't have any values there. We're going to define it as 0. Sensible. Okay, what do we do in the other case?
Max of left and right.
Say that again. Say that more loudly.
Max of left and right.
Max of left and right and plus 1 because of our node as well. Okay, good. So 1 plus max of left and right. We're all on the same page now? Questions? Good. I don't want any questions. Great. Okay. So now we know how to define the height. Okay? We have to define what it means to be balanced. And we're going to want a slightly liberating definition. We're going to say that a tree is balanced, so now this is scare quotes balanced, as long as, and this property is true recursively, just like with binary search tree, right? It's got to be true everywhere in the tree. The height of the left and the height of the right are equal or off by 1. Okay? Equal or off by 1. At every level, they're equal or off by 1, and I'm going to allow it to be off by 1 on either the left or the right. Does that make sense? Now, this is not exactly that recurrence, but it's close enough, and if you work out the mathematics of it, you will find that this also gives you the logarithmic behavior that you want. Okay? It'll just be a log with a slightly different base. Math people, go think about it. It's a fun exercise. Not math people, trust me, and I'm right about this, so you can trust me on this, okay? Unlike last class, you should have trusted me at the end of last class, but this one you can trust me on. Okay? So we're going to give ourselves a slight amount of imbalance, but we don't allow excessive imbalance, right? Because the whole tree must also have this property. So it's not like, oh, I can have a, because otherwise I could do this, right? I have I have a node over here, and then, oh, see, this one, it's off by 1 over here, it's off by 1 over here, it's off by 1 over here, but over the height of the tree, the whole thing degenerates into essentially almost a list, right? So that doesn't work. We can't allow it. We have to have it at every level it's true, and it's true at the root as well. So this one, for example, what's the height of this? 1. Height of this is 2. Height of this is 3. And so this is not a balanced binary search tree by our new definition. Good? Okay. So we want to make balanced binary search trees by this new definition. And we're going to do, so I've just shown you I've shown you a trick now, right? Which is you relax your definition a little bit. Notice that what that also does is it lets you have things that are not all just sizes of powers of 2. Because otherwise we'd have that problem. So you can ask yourself, again, if you're a mathy person, ask yourself, what are the sizes of trees this does not let you get to? What are the sizes of trees it does let you get to? Fun exercise to think about. So, we're giving ourselves the ability to represent more than just sizes of powers of 2 trees, and we've given ourselves a little bit of wiggle room, which will turn out to be critical for what I need. Okay? So, remember, most of the things we're trying to do, like look up, don't care, the only thing that's actually a problem is insert. Insert's where the whole problem is, right? Insert is the thing that creates degenerate trees. Once the tree is created, we're fine. We're going to use another technique that we will sometimes use in computer science. There are 2 ways to think about this problem of insert. And right now, it might not even be obvious to you that there are actually 2 ways to think about it. So let me tell you what they are, and then you'll be like, duh, of course there are 2 ways. One way is to say, remember, this is an invariant, right? It has to always be true. That's what invariant means, literally. Does not vary. It is always true. So one thing you can do is to say, well, let's define an insert such that when it's given a balanced tree, balanced by this definition, produces a balanced tree. That's what you would expect, right? You would expect me to say, insert takes a BBST and an element, and it produces a new BBST. What else would it do, right? And right now we have the problem that even if you give it a BBST, the output might not be. Okay? And you can define this, right? Just take our sorted list and it does that. It's initially balanced because the empty tree is balanced. The first thing we add is still balanced because it's off by 1, but the second thing we add, it's no longer balanced. So we could define a more complicated insert. It turns out there's actually a nicer thing to do. And if you really want to stretch your brain a little bit, go think about how you would define that insert. And if I had plenty of time, I would try to develop it in class, but I'm not going to because I have only so much time to cover this topic. We'll instead do something a little sneaky instead. And this is a thing, an idea you will see over and over again in computer science. This is ultimately what insert is going to do, right? So we'll call this the true insert, right? Because if we don't get a BBST at the end, then we're hosed. None of what we've talked about applies, right? So we have to do that in the end. But instead what we're going to do is we'll use the old insert, right? Which takes a BBST and an element of whatever the type is that the tree is over. And it produces a almost BBST. So insert is the normal insert that we already have, the one we've defined before, old insert. Old bad insert, right? Which imbalances trees. And then we'll define balance to take an almost BBST and balance it to produce a BBST. Okay? That's the game plan. You have no idea how to do any of these things, right? That's okay. But the game plan is we'll use the insert that we had before. It's going to produce slightly imbalanced BBSTs. We'll then write a balance function that takes that and turns it back into BBST. And as you can see, the composition of these two things gives us the good insert that we want that preserves the invariant of balancing. Make sense? Just as a game plan. I'm told you how to do it. Yes?
Is it important that almost BBSTs aren't just BSTs?
So there's a question of what is an almost BBST, and I'm going to get to that. Okay, so the twiddle is meant to be roughly, right? Kind of like rough nums have the twiddle in front of them. It's roughly a BBST, and I'll tell you exactly. I have to be very exact about this, otherwise I can't write this and none of this works. So I will be exact in a moment. Okay? Another hand went up somewhere around there?
Same question.
Same question. Good. So what is an almost BBST? Right? So the tilde is because it's kind of, that can almost be. So it's two things. It is a BST. We never violate that. Right? But that's okay because old insert was producing BSTs, right? That wasn't a problem. That was not our difficulty. Right? The other thing is, you remember we had a balance factor and we said it could be off by 1. We'll allow it to go up to off by 2. Note that what that means is we have to make sure that we call balance after every insertion. Right? A balance that works for off by 3, I don't want to have to think about it. The off by 2 will be interesting enough. Off by 3 is going to be really complicated. Right? But off by 2, what you can think of is basically you can think of calling this as rebalance, or another word you might want to use is repair. We've slightly broken our BBST and we want to repair it. You see that? So that's our game. We'll keep our old insert. What is the worst our old insert can do? Assuming that it inserted into the side where we were already off by 1, it could turn that into off by 2. Right? It can make, there's a height of k plus 1 over here, a height of k over here. I add something, this becomes k plus 2. If it inserts in the worst possible place, then that's why the sorted list is always a useful intuition, right? The first insert is fine, but the second insert, we were off by 1, the second insert is now made it off by 2, and that's what we have to fix. You see that? Questions about that? Okay, so what we're going to do is define a very narrow kind of repair procedure that simply takes things that are off by 2 and turns them back into at worst off by 1. I mean, if we get it completely balanced, that's just fine, right? But we've given ourselves this slack. Questions? That's the game plan. That is the rest of class. We're going to have to figure out how to rebalance so that off by 2s become off by 1s. Okay? All right. Simplifying assumption without loss of generality, as mathematicians like to say. It doesn't matter whether I'm off by 2 on the left or on the right. Right? Because the same thing that I do will work symmetrically. Right? Nothing I'm going to do is depend on whether it's left-hand side or right-hand side. So I'll just show you the left-hand side case, and from that you can figure out the right-hand side case. If you have trouble, buy a mirror. Okay? Good. So, what's our situation? We have a tree, and so I'll try to follow the following convention. I also use this in the textbook. I'll use lowercase letters to refer to individual nodes and uppercase letters to refer to whole trees. So I'm going to assume for the rest of this class that the insertion is happening on the left. So that means the new value that came in ended up going to the left and causing the left subtree to somehow become imbalanced. Right? So, what do we know about the height of this tree before insert? Before insert, what do we know about the height of this tree? relative to the height of this tree. Let's say that the height of this tree is k. What do we know about the height of this tree before insert? It must be,
At least k or k plus 1.
what are the possible things it could be?
Minus 1.
So it could be k minus 1, could be k, it could be k plus 1, right? Those are the things the balance factor allows me to do. If the height is k minus 1, am I worried about this? No, because what's the worst it can do? It can balance it. If the height is k, am I worried about this?
No.
No, because the worst it can do is? No, balance it, because I redefined balancing, remember? Aha, trick question, right? Because balance for me is I'm allowed to be off by 1. Balance, right? So it can balance it. Okay? So we don't worry about this case, we don't worry about this case. Here we're already at the limits of our tolerance, and adding this might work. There might be room in the tree. It might go to the left child, to the right child, to the left child, and there might be room there, right? We're worried about the case when it's not. So we're worried about the case where this turns this into a k plus 2. Okay, I see 2 hands up. Hand there, hand there.
Wouldn't you have to worry about the k minus 1? Because if it enters on the other side, it would be k minus 2. It's like where if the left side is k minus 1, and then you enter another one on the right, so the element goes on the right.
No, but we're assuming the insertion's going to the left.
Oh, okay.
We're specifically assuming, that's okay. Specifically assume, that's good, it's fine, I want to make sure everyone's on the same page. Specifically assume inserts on the left. At the end of this process, we're going to be given a BBST. If the next insertion goes on the right, we'll deal with that separately with the mirror, okay? Good? Okay. Question? No, back there.
We still have to balance the entire subtree too, right? Because like in the k minus 1, you could say you had like that subtree had left subtree that was one longer than its right subtree. Then
Yeah, good. So the point is we might have to do this recursively, right? I'm just talking about what happens at this level, and then the same thing might have to be done at every level below that. Good. Right? Because we don't know what that insert is going to do to the invariance below it. Right? Good. All right. Any other questions? Okay. So our case that we are interested in, we're interested in the case where by process of inserting an element into the left, we have now made the height of the left subtree k plus 2. That's the case we're interested in. Okay? Well, how could it be k plus 2? Notice, by the way, if the size is k plus 2, we know that this is certainly not the empty tree. We don't know. K might be the empty tree, right? But k plus 2 means it's most assuredly not the empty tree. There's got to be at least one thing. In fact, there's got to be at least 2 nodes in there, right? 2 height of 2. So what I'll do is I'll bring in my little X-ray vision and zoom into this tree a little bit. Okay? So clearly we have a node here, which I'll call Q, and that node has 2 subtrees. Okay? So Q is this node, A is the left subchild, B is the right subchild, and C is that whole tree over there. What can we say about the heights of these things? What do we know about the height of A and the height of B? After insertion, remember we've inserted, right? We're in this case, we've done the old insert, we've somehow screwed up our BBST a little bit. We're now in the repair case, right? So insertion has happened. The height of this is how much now?
K plus 2.
K plus 2. That's the case we're interested in. Okay? So what is the height of A and what is the height of B?
K plus 1.
Anything less.
What do we know about them? Talk to your neighbors and come back and tell me. What do we know about the heights of A and B?
So K plus 1 it can make K, it's not assuming that like wait, we know the whole thing. So one side is clickable. The other side is not. Why on the other side. So it used to be k plus 1 and k. We inserted on one side.
In 5, in 4, in 3, in 2, in 1. Let's go. So, what do we know about the size of A and the size of B? Size of A, size of A. Well, let's do pairs. Let's do pairs. Where did we last stop off? Somewhere. How about we start there? What can you folks tell us about the size of A, size of B?
Well, one of them has to be k plus 1 in order for the whole subtree.
Yeah, if neither of them was k plus 1, we'd be done, right? So either A's size is k plus 1 or B's size is k plus 1. Okay? Okay. Anything, next pair? What can you tell us? Relative to that, can you tell us anything?
That, well, we said that one of them has to be k plus 1 as well. And
Yeah.
maybe like the other one could be k plus 1 or
They
k.
can.
So the other one, so if A is k plus 1, B has to be, does it have to be k? Can it be k minus 1?
Yes.
Why?
Because
Because previously it was balanced, now it is imbalanced, right? The whole point is we're in an imbalanced state, right? So B could be k or k minus 1, and similarly if B is k plus 1, A is k or k minus 1, right? Is that consistent with what all of you are thinking? Good? Okay, because that's what it means to be imbalanced right now. But if it was not the case, then why can't those also be k plus 1? That would be fine, right? That is, let's take this case. A is k plus 1. Can't B also be k plus 1? That's perfectly consistent with this tree's height being k plus 2. Perfectly consistent. So why can't B also be k plus 1? New hand. Somebody who hasn't spoken in a while. Who hasn't spoken in a while? Yeah.
Because you've only inserted one element.
Only inserted one element. If it was already k plus 1, then it must have been the case that we've already had an imbalanced tree and our whole assumption that we've inserted one element must be false. Okay? Yes?
So when we're counting the height of this tree, why don't we count P?
Because it's not interesting for what we're about to do. Okay? Well, we'll see. Don't worry. P's not forgotten. I appreciate no node left behind. We'll take P back out. Yeah? The point is, P doesn't affect the invariant about the left and right side, and that's why we're interested in the invariant of the left and right side. You'll see P come into play. Okay. So here's the thing. This is too many cases to think about, right? All of these different possibilities. So let's split the world into two possibilities. Let's do this case and then this case, okay? It'll be much easier because then we still have two cases to worry about in each case. Yes?
Why are we dealing with the case where B is k plus 1? Like, aren't we always assuming it goes to the leftmost? Or is it just to the left?
I'm sorry, it was just to the left at the beginning. From P's point of view, it went to the left. That's all we were assuming. We don't know from there which way it went after that. Okay? Make sense? Great. Okay. And as you noted, this is a recursive issue, right? Like it could be, P could be some subtree, somewhere down some value may have shown up and we're talking about balancing some subtree. Okay? So let's do this case first. Let's assume that A's size is k plus 1 and B's size is either k or k minus 1. Okay? What do we need to bring everything back into balance? Well, let's now do another piece of analysis. Okay? Let's figure out, remember, is this a BT? Is everything we're looking at on the board a BT? Yes or no?
Yes.
Is it more than a BT?
Yes.
What is it?
BST.
It's a BST. Therefore, we know something about all the values in the tree. Right? We know something about the ordering of the values. Talk to your neighbors for a minute and tell me what you can say about the ordering of the values between A, B, P, Q, and C. Go.
You know, smaller than everything is B's relative A to, and you know that A and B are both small. Not necessarily.
Make like the last value in A times Q goes to B. Yeah.
The root of C is greater than
All right.
Q is less
The largest value.
5, 4, 3, 2, 1. We're back. What can you tell me about the ordering of the values? The ordering of the values, ordering of the values. Yell it out, yell it out. What can you all say? Everybody can say something with the ordering of the values. Do we have a total ordering if we just think at the level of the trees?
Yes.
What is the total ordering? Yell out the total ordering.
A is less than Q is less than B is less than P is less than C.
Everyone. You don't even have to say less than. Just yell out the letters in order. Everyone.
A, Q, B, P, C.
I think I heard everyone say the same thing. Good. Okay. Now, in International Phonetic Code, so we don't get any confusion. Sorry. Okay. Okay. So, alpha less than
Quentin.
Quentin? Quebec. Less than Bravo less than Papa less than Charlie. Okay, good. If you ever need to call an airline and read out your confirmation code, do it in phonetic code. They love it. They're just like, it transforms the experience. They're like, oh, I'm dealing with a professional. It just gets so much better service. Okay, so phonetic code, really useful. Memorize it. And pick the NATO one. Don't go making up Quentins and stuff. So, alphas, so everything here is less than this. If this is less than this, but all of these are less than P. Remember, this is the thing we talked about last class, right? It's this recursive property, and if you're not careful in how you define it, you could end up with this if you just do it locally. All of this is less than this, and this is less than everything here, okay? And I'm using a shorthand, obviously, I mean all the values in the trees. Good? Okay, well, then we can make the following observation that somebody else made in about 1959, a pair of Russian mathematicians made in 1959. They said, look, this tree is too tall. This tree needs to go up. I mean, tall trees go down, but we're computer scientists, so our trees are going to go up to become shorter. Okay? Does anyone know what Mass MoCA is? Yeah. Mass MoCA is the Museum of Contemporary Art for Massachusetts. It's out in the western part of town. It's like near Williamstown, basically. It's North Adams. And it has this amazing exhibit, which it's this truly spectacular thing. It has these trees that are in planters and are pointing downward. They're like suspended in the air. Okay? It's the only place in the world I know where computer science trees exist in practice. But except the trees have realized this is kind of screwed up, and they're kind of like growing kind of back up, and so they're not even, yeah, so there are no computer science trees. Okay, so we need to take A up, okay? And we need to somehow bring B down, but also notice that C is at the wrong height, right? Part of the, you can blame the mismatch on A or you can blame the mismatch on C. It's like, hey, C, you need to get down a little bit, right? Well, so the observation is, what if instead Q were at the root? Then we can put the A subtree over here. Because A is less than Q. Okay? Now, over here, we're going to put P, which is okay because P is bigger than Q. What lies between P and Q?
B.
B. Now what lies here? C. What is the height of this tree? Oh, we're not done. What is the height of this tree? This tree's height is K plus 1, right? This much is K plus 1. K plus 1. What's the height of B? K or K minus 1. What's the height of C? K. So, are these two balanced?
Yes.
Yes. What is the height of this whole tree?
K.
K plus 1.
No, K plus 1, yeah.
K plus 1.
It has to be.
Height of the tree. K plus 1. right? It's this plus this. This can only make it k. This doesn't matter. So it's going to be either, if you count from here, it's going to be either k plus 1 or k, but this is already k, so the whole thing is k plus 1. What is the size of the left subtree? What's the size of the right subtree? Voila, you are done. Okay? These are called AVL trees. Adelson Velsky is the first guy's name. Landis is the second person's name. Adelson Velsky and Landis discovered these, and they're called AVL trees. Okay? Now, in the computer science literature, you'll see other things called red-black trees and so on. There is a difference between these trees. AVL trees tend to be taller. Red-black trees tend to be bushier. They tend to be kind of wider, right? There's something called 2-3 trees as well. Like, why stop at 2? Why not have 3 children? And then that gives you some gaps to put things into, right? So there are 2-3 trees and red-black trees. Those tend to be bushier. These tend to be taller. In many cases, you like bushier trees because then the actual number of nodes you have to go down is less, okay? But they tend to take up a little more space. AVL trees tend to be a little taller, so the number of nodes you need to traverse to find something may be a little longer, but they tend to take a little less space. So it's really a trade-off between space and time. Usually people say, the space isn't too much of a problem, and we'll take the trade-off in time, fewer number of steps to get to my node, right? Because essentially if you can have a log base 3 instead of a log base 2, that's better, right? Log base 2, 3 essentially. But sometimes when you're space constrained, this is actually a lot better, because you don't mind trading off a little bit of time, but you don't have a lot of space to give embedded systems, things like that. Okay? Okay? Good? Everyone see this? Essentially the insight here, think like a mobile, like a kid's mobile. You have these things that are balanced, and this one's hanging off this way. And all you've done is you've just picked up the tree from here. You just picked it up over here, and then this node attached over there, and this thing's still dangling off the side, and now everything is balanced again. That's really clever, right? That's really clever. Okay, so we checked off this case. Now, I want you to talk to your neighbors and do this case. So now we flip things around. So, has anything changed about this? No. Nothing's changed here. Okay? But now we have that this has size k, this has size k minus 1 or k. Go. What? K plus 1, I'm sorry. You should have just said you were done, come on.
No, you can't, because B is in there. Wait, let's try that. What do you mean?
Draw pictures and put labels of the heights, otherwise you won't get this. Draw pictures and put labels.
Yeah. So like let's have this. You know that is lesser than no. You know is lesser than Q. What do we need? This guy needs to work, this guy needs to back down. He's down. Yeah, it's up.
B plus 1, which like that.
Just go Q goes to A, and then T and B goes to
Look at the exact same
And K with K. So
Q can't go to B, and Q can't go to B.
In 5, in 4, in 3, in 2, in 1. We're back. I'm gonna guess, let's do a little vote. Hum if you are done and you're sure you got it. Yeah, that's what I expected. Let me give you a hint. Okay, this is what I found useful for doing this. I found it very useful for breaking B down, just like we broke Q, this node over here. Break down B into two subchildren and think about what those sizes are and what those values are. Otherwise, it's really hard to reason about this. Okay.
One of these doesn't exist. Oh no, these can be plus 2. Just shift this so Q's on top again.
So that would like
the subtree, let's see, and then how do we label all the other ones around?
oh no wait, no. I did it in the height.
Oh, that's
No. B is B1.
So R has to be on top.
Right, I think yeah, we have,
But then there's nothing less than Q. Unless you go to unit A. What's that
I know that not necessarily that good. You've done a B1, the B1 is greater than that. I would work for that. Which oh wait, one second. You know that. So P and P, if this is P, you can have either B1 A or
What is it minus
what is less
All right, in 5, 4, 3, 2, 1, we're back. So here is a thing we could think about doing. Okay? So we'll move this up a little bit. So we'll put R over here. Okay? And so R now has on its right, it's got D, and it has on its left Q. Okay? So we have A over here, and we have C over here. So A is less than Q, Q is less than C, all of that is less than R, all of that is less than D, all of that is less than P, and all of that is less than C. Do I have two C's? Oh wow, that's the way to confuse you folks. E, how about E? Okay? Okay? The C's, yes. Okay. Okay? What is the height of this?
K.
Height of this is K. What's the height of this?
K.
D is K.
Wait, it says it right there.
It says right there.
I know that.
B was K plus 1.
Yeah.
Oh, yeah, one of them can be K minus
We took out one of the nodes, right? So the worst case this can be is K, because then we've got K plus 1, K plus 2 versus K. Okay? So, this is K. A is K or K minus 1, right? And this is K. So we haven't actually fixed anything.
Yeah.
Yeah, but now we have.
But we now have the previous problem. So this could be, one of these could be K minus 1, and so both of these happen to be K minus 1, and that's your K, you're already done. Because you moved the nasty part, which is this, so this could be K minus 1 actually, right? This could be K minus 1, but they can't both be K minus 1, otherwise you haven't solved the problem, otherwise you don't have a problem. So to have a problem, one of these must be K minus 1, one must be K. If this one is K, this is K minus 1, you move this down, you move this up by one level and you're done. If not, because now you have two K minus 1s over here, right? And so that becomes K, K plus 1, and that's okay with K. Otherwise, that's still, if this one's the problem node, but now we have an imbalance of 1 in this case, and that's exactly the previous case that we solved. Now done. And that was really fast, but it's all written down in the textbook. So go read the sets chapter in the textbook, and now I've finished the chapter. And now we truly are done with what I promised we were done with last class. We really, really are done.